Hello, my name is John Gabriel and this is a new calculus channel. Today I'd like to just touch on two topics which are actually a response to a couple of my viewers' questions. So I don't know if you're aware, but recently I created a series of videos showing how to derive the 5 requirements, not the axioms or postulates. And one of the questions was, well, how can you have many circular paths from which the distance from the path to the center is always the same? Shouldn't it just be the circle? Well, no. There are innumerably many paths from where you can have the same distance to a center. And so let me show you how it works. So if we have, for example, that's the center there, that red dot. And all these red lines here are actually equal in length. They're all radii, okay? Then if we just join these up as arcs or geodesics, a geodesic is the shortest distance on a globe, then this green path here, from anywhere on this green path, the distance to the center is the same. So it has a similar property to the circle. There's one difference between this and the circle, though. Only the circle has the shortest path if we start at one distance and we come back to the same distance. All right? So, and that circle will be the same as a great circle, either a great circle from north to south or a great circle from east to west. So there are innumerably many paths which have the property that from the path to a center, the distance is the same red straight line. But the circle is the one which is produced from uniform motion and direction, and it has the shortest distance. So it's kind of difficult to think about these things, but believe it or not, the ancient Greeks actually knew these facts, and this is why they derived the circle in a very specific way, using a point and a straight line. Okay, so that was one of the questions. And the other question was, well, all angles that are subtended on the same arc must be of the same size, right? Well, if we look at these two angles here, they're vertically opposite, and they're not actually subtended on the same arc. So, but they're equal. Is this an exception? Turns out it's not really an exception, because if we move, what they mean is if we have the angle at the center. See, so if we bring the angle at the center, like so, then the arcs, well, you get the idea. Then the arcs are exactly the same size, right? So, this here explains why angles subtended on the same arc are equal. And of course, this here can be looked at in terms of the property where angles at the circumference subtended on the same arc are equal. But generally, we always talk about angles with a vertex at the center, and that's how it was derived in ancient times, or that's how it was thought of by the ancient Greeks. So those are two questions I just wanted to answer, and I'll try to answer more. I do not promise to produce special videos like this, but sometimes it helps and sometimes it doesn't. Well, hope you enjoyed this little presentation. My name is John Gabriel, and this is a new calculus channel. Goodbye.